Okay, let me go in full screen, see if that works. Can you see the presentation?
We see the presentation, but not in full.
Not in full screen?
No. You might need to stop showing and start showing again.
Okay.
Blinked, but there's still not full screen.
And now?
No.
Looks like you need to hit the full screen icon in the PowerPoint. There you go.
Yeah,
you got it. Yeah, you got it.
Is it better like this?
It looks perfect now.
Okay. I didn't do anything. Don't understand. That's okay. All right. So Dave asked me yesterday to give you an update on the status of the V1 water cycle model. And today we'll be specifically focusing on the low-res version of the model. So this is the coupled water cycle model. We will maybe have another presentation at some point in the future focusing on the status of the high-res model. So this is not my work. This is really the work of the entire team, in particular the water cycle couple simulation tasks, but extending beyond to all the E3SM groups that have contributed to the various model components. But I would like to mention a special thanks to John, Mark, and Luke, who have been working very hard over the summer to improve the MPass Ocean. You know, you probably are aware that we had the so-called critical path meeting to address what were perceived as critical issues in the ocean. And they have really worked very hard and spent a big chunk of their summer in what I call the trenches of model development. And hopefully they have not been too traumatized by the experience. And you'll see the result was really worth it.
Thanks. I'd like to add a few names to that. Philip Wolfram also spent a significant part of his summer, and really all the ocean modelers here, including a postdoc named David Lee.
Thank you. So the current version that I will be showing today is a brand new version that was started just not long ago, 2 weeks ago maybe. It's a derivative of the beta 2, but it has some additional fixes in the ocean that came very recently. And we'll have more description on those fixes at a future couple telecon. But they basically, so this is what the FCT2 stands for. It's a fix. It's to the flux correlated transport scheme in MPass Ocean. The full name of the experiment is this. This is roughly the date at which the simulation was started. This is the nickname FCT2. And this gives you the comp set and the resolution and the machine is run on. So it's a Acme water cycle simulation for 1850. S stands for the fact that it started from a spun up ocean and sea ice from core simulation. And the resolution is a NE30 atmosphere OEC V3 ocean grid. So this is the 30 to 60 ocean grid. And it's being run currently on Anvil. And John Wolf is running that simulation. So in terms of what's new in this, as I already mentioned, lots of improvement over the summer in MPass Ocean, as well as some bug fixes in the atmosphere, mostly related to MG2 microphysics. But most of the changes were in the ocean. And that simulation is currently running, pre-industrial control, 1850. And as of yesterday, it was a little bit beyond 50 years. So I'll be showing results from that simulation. I made a very similar presentation last week during the advisory committee meeting, but at that point I was using the previous version, which was the official beta 2 at that time, and that the new simulation is superior to the previous one, so I updated all the figures yesterday, or most of the figures. Here is just a couple of figures from Mark Peterson of before and after all the ocean improvements that went into the model. This is profiles of vertical profiles of salinity near the equator, before and after. Before there was a lot of struggle with vertical noises. You can see that it has all been solved and the profiles are much more realistic. And this was not at all easy because one of the manifestations was noise in the vertical. So a lot of time was spent looking at vertical mixing naturally, because this was thought to be the root cause of the problem, but it turned out that it wasn't. And it was related to horizontal noise that was also discovered. You see before, there was a fair amount of green noise. In here is the salinity. And after that was corrected. So it turned out that most of the problems were related to the advection that was creating some noise. And the ocean team can provide more details. Mark Peterson created a very nice page that you can find on Confluence describing the changes.
Would the solutions look different using the code version that we have with FCT fix versus what you're showing in the plots here?
The ones on the right are with what we're calling FCT2 a few slides ago.
Okay. Okay, great.
So this is top of the atmosphere global average net radiation over the course of various simulations. So let me walk you through some of them. The purple line here is V0.4, so this will serve as a reference for us. This is the simulation that was done by Marsha and Kate. And then we have a beta 1 version in orange, essentially with the beta 2 version in green, and the newest beta 2 FCD2 in red here. So all the simulation initially have an adjustment in terms of net radiation, going from negative and then stabilizing after 20 years or so. And you can see that the FCD2 simulation is actually stabilizing very close to a net radiation of 0, versus the beta 2 was at a higher radiation imbalance of around 1. So that's good. After initial adjustment, we're getting close to the energy balance. Now that might change because there's a couple of things we have to adjust in the atmosphere. In particular, the energy fixer, I think, was not turned on in this latest simulation. So we'll try turning it on and see what happens. In terms of components, shortwave and longwave, this is the same time series plot. The FCT2 simulation in red here has a global average values around 243.5 or so. So this is a little bit higher than the observations. The observations are around 241 for both long wave and shortwave. We may want to try to do a little bit of retuning in the atmosphere in terms of increasing cloudiness to try to reduce those two numbers. But this is not something that would be a showstopper. Even if it turns out that we cannot do any further retuning, I think this would be acceptable. Now, the evolution of the global surface air temperature, and most of you probably recall that we have struggled for a very, very long time with an initial coupling shock, where when we would take initial conditions from core simulation and then start the couple model from that, there would be a very large initial drop in surface temperature, as you can see, for example, from the orange line here, which is one version of the beta 1 model. Now, we do expect some drop initially here because the initial conditions from core are for present day conditions, and we are spinning up a pre-industrial simulation. So we do expect some cooling, but this was a very large cooling. You can see it was cooling by almost 2 degrees. And that is something that has been consistent for at least the past year or more with any couple simulation than we did with MPAS. And for reference, this is the cooling that we had with V0.4, which was also significant, but probably that was acceptable. This was a little bit of borderline of what we would consider acceptable. Now, the latest simulation shown in red here, you see has a cooling, but only lasts 10 or 15 years, and then it stabilizes around 13 point something degrees Celsius, 13.3 maybe. And this is just about right, because the global surface air temperature for the 20th century is estimated to be around 13.9 or 14. So we do expect this to be cooler because it's an 1850s. So we do expect it to be several tenths of a degree cooler. So this is very much on target what we would expect for pre-industrial conditions. And this is really, really a huge accomplishment from the ocean team. This looks like just one plot, but this is, we have never ever seen a V1 configuration that produced anything like this until the simulation that is currently running. So that's an amazing accomplishment that was done here.
So Chris, are you going to show a horizontal distribution of the SST?
Yes, just a second.
Okay. Sure. Thank you.
Just for reference here, this is each gray line here shows the global air surface temperature of various CMIP5 models, and this is the absolute temperature. Usually when people do model intercomparison, they normalize in some way, but this actually gives you the spread of the actual temperature among the CMIP5 ensemble. And you see there's a very large spread from 12 to 15 Celsius, but most of the models are around 13.5 or a little bit below. And I put a star here estimating where beta 2 FCT2 would start, and we are pretty much right where most of the models are. So this is great. So this is Xiaocheng, the figure that Xiaocheng requested. This is the difference between model and observation for SST, and I took the climatology from years 31 to 50 of that beta 2 FCT2 simulation. So red are area where we have a warm bias, blue areas where we have a cold bias. And this is relative to the pre-industrial estimate from the Hadley SST dataset. And you see patterns that are quite familiar. Warm region near the coast, near in stratocumulus region, we'll get back to this later, and then cool region in the North Atlantic, North Pacific. What is notable is the mean bias here, minus 0.4. That is, again, a very, very big improvement compared to what we had before. It's still a little bit cold compared to the Hadley estimate, but it's much, much better than what we had. We used to be around minus 0.7 or so. And that improvement in the mean bias results in a much improved RMS score of 0.98. Before, we always were around 1.2, 1.3. And that is a very big difference. So around 1 or below 1 is starting to be a very good SST field. This is the evolution of the sea ice extent, northern hemisphere, southern hemisphere, comparing the present day climatological observation in black, and I highlighted the present day seasonal cycle here, comparing beta 2 FCT2, I forgot to change the label here, and V0.4. And you see that it's reasonably steady. We have the INO cycle is a little bit more pronounced in the southern hemisphere. We have larger maximum and maybe slightly larger minimum as well. But the southern hemisphere is quite steady. The northern hemisphere is also relatively steady, except near here. There's a little bit of trend. I'm getting just a little bit nervous to see if that trend continues, but hopefully it will not continue and we will not have any dramatic change in sea ice climatology in that control simulation. But so far, it looks reasonable, as I can see. This is AMOC, the strength of AMOC, which is very important for the ocean circulation. And so we have a value of around 14.5 spread reps. And that is also better than, that is very close to the observation. And it's much better than any previous version of prototype E3SM V1. So that's a huge improvement as well. Beta 2 was already quite good, but it was around 13 or so. So this is further improved. And it looks steady, so hopefully AMOC will continue. Those are the PCMDI metrics plots, also sometimes referred to as Gleckler plot. And we have used them to kind of estimate where we stand relative to previous version of E3SM, as well as some subset of CME5. And I'd like to mention that Chi-Tang stayed late here last night to update the figure with the latest simulation, and you'll see that it was worth the effort. So here is a subset of CME5 model. I don't know exactly how they were selected. It's not the entire set. And each box shows a specific variable. The bottom one is precipitation and a specific model. And then in each box, you have 4 triangles, which represents seasons, DJF, and so on. And the coloring is a measure of the relative scale of the global RMS compared to the entire ensemble here. And the warm color, yellow to red, mean that the model is performing worse than the ensemble. And the blue colors mean that the model is performing better than the ensemble for the global RMS for the particular variable. And this is also using, for FCT2, it's using the last 20 years climatology. So V0.4 here is a very good model. You see a lot of blue and a couple of areas where it's kind of middle of the road, but overall it's an excellent model. And we know that we started with the CSM version that was very good. And then those are a few versions of E3SM, Beta 1, Beta 2. This was a sensitivity test on Beta 2, and this is the latest and greatest Beta 2 FCT2. And you can see that we have a lot of blue here. And other areas where we used to have warmer colors have gotten better. 850 temperature, surface air temperature, they both got substantially better compared to, say, Beta 1 or Beta 2. And even the 500 hectopascal height, which we have been struggling for a long time, also got substantially better compared to, say, Beta 2 or Beta 1. You see a very large improvement. Some of that is due to the improvement of the temperature. So overall, this is, I think, is very encouraging. It probably will not be the best of the CME6 model, but this is the first version of E3SM, and I don't think anybody really realistically should be expecting that it will be the best model. But it has this V1 has a lot of new features, and I think we will be very competitive compared to the rest of the community. You can see there's a lot of white here. I assume all those models will get better, but compared to CME5, we are definitely average or above average. Now looking at a few actual fields, starting with the net radiation at the top of the atmosphere. And I'm comparing year 31 to 50 for Beta 2 FCT2 and year 81 to 100 for the reference V0.4. So it's not exactly the same year, but it's a perpetual 1850, so it's acceptable. And the panels here shows you the difference between the model and the observation. The observation are actually for present day but that's okay because the error between the model and the observation is still much larger than we estimate the change between present day and pre-industrial. So you see that the two figures look very different. So we have a very different model. We have regions where we have significant improvement. For example, many land areas have improved. We have a reduction in biases for Eurasia over Africa. We have significant improvement overall over the Southern Ocean in terms of net radiation, and significant changes over the maritime continent. We had large biases over land that have been reduced, but there have been various other tropical biases that have come. The largest degradation is related to the stratocumulus region here, where we have insufficient reflection from stratocumulus cloud. And this has been a known problem in the V1 atmosphere. Looking at the score, we have an RMS of 9 versus 9.6 with V0.4, so there is a slight improvement. Now, focusing on the cloud pulsing at the top of the atmosphere, you see some of the same features. So clearly the efficiency in the net radiation in the stratocumulus region comes from the cloud. It's not a surprise. You see some improvement over the tropical region, but we still have biases there. You see large improvement over Africa, for example, over South America as well. I think a significant improvement. Some degradation over North America here. But overall, it is still much better with RMS of 10.3 versus 12.94. Then we can break this figure into shortwave and longwave component. Shortwave, obviously the stratocumulus are showing up there. They are low-level clouds, so they affect mostly shortwave reflection. And we also have some large bias near the maritime continent with excessive and lack of cloudiness there. We'll see some of that signature in the precipitation in a minute. And then the North America biases there seems to be mostly a shortwave story. But you see that it is still improved compared to V0.4. Focusing now on the long wave cloud forcing. In this simulation, we still have a fairly large mean bias. That will be one target of improvement for some minor retuning that we plan to do. So the mean bias in long wave cloud forcing is around -0.5. That means we generally don't have enough long wave trapping from clouds, especially in the tropics and over the warm pool here, where you have large regions with blue values indicating that this is a region of deep convection, and so that is indicative of a lack of cirrus cloud. So we have too much long wave coming out because we don't have enough high clouds trapping the long wave. So that is somewhat degraded compared to V0.4. And I'm hopeful that maybe we can make minor tuning that will improve this a little bit. And Pudrun has made some suggestion of parameters that we could adjust to try to get more cirrus clouds. So we'll try them there. Now this is the precipitation. On the left here, you have observation and different model, and this is the difference. And you see overall both model, beta 2 and V4 have a double ITCZ. This is not surprising. This is characteristic of all couple model. You see the double ITCZ here, and you see it as the excessive precipitation across on the equator. The precipitation in V1, beta 2 FCD2 is still slightly worse than it was in V0.4. RMS is larger, and then we have excessive precipitation really just focus on the maritime continent, and then a lack of precipitation further. And Amazon is a little bit worse as well, and a little bit more excessive precipitation over high elevation here. So it's some degradation. We I'm planning to do a few more tweaks of the convection, and that may improve a little bit, but I think realistically we will not be able to match or beat the V0.4 precipitation. Nino 3.4, this is something that has been giving us a lot of grief over the last year or so, and this is the time series of Nino 3.4 index, 40 years of Hadley SST versus 40 years of the model. Please note that the vertical axes don't have exactly the same range. I think they may have the same range on the positive side, but they don't have the same range on the negative side. But you see overall that this is much, much better than earlier version. We now have some significant variability. We have some large events above 2, for example here, and maybe this one too. As you can see in observation, that happens every now and then, large event. We have smaller events. We have La Nina event, although they are not quite as strong as they are in the observation. And the frequency doesn't look that far off. It tends to be a little bit on the short side. We'll see later on the spectrum. But this is much better than anything we have seen before with V1 prototypes. This is comparing the amplitude of the Nino3 and Nino4 SST standard deviation against observation and CMIP3 and CMIP5 model that was compiled by Bellinger et al. 2014. On the Bellinger figure, I just added a line for the estimate of beta 2 FCT2. For Nino3, we are a little bit below the estimated standard deviation, but within the range of typical CMIP model. This is the ensemble of CMIP model, and those are individual model. And for Nino4, we actually have slightly more standard deviation than observed. So our El Nino signal is shifted a little bit more towards the Nino4. This is also much better than what we had in previous version. The spectrum, this is the full record of the spectrum from Hadley SST. This is 40 years, which had a stronger overall El Nino. And this is what we have so far. This is only a 50-year simulation, so some of the longer periods here are not very representative yet. But we do have power above 95 or 99 confidence level. It's weaker than the observation, but we have power. We may have a little bit, and on the frequency, it may be a little bit skewed towards the shorter periods rather than the longer one. But it's much better again than what we had before. And hopefully when we have a longer simulation, we may have a little bit more power here. So this is my last slide in terms of what we're planning to do in the next few months. It would be good to have more eyes looking at this beta 2 FCT2 simulation. So if there is anything that is worrisome or problematic, we find out before it's too late. As I mentioned, we're going to attempt to do some minor improvements to FCT2 by retuning some parameters in the atmosphere to try to both reduce the mean bias in long wave cloud forcing and maybe improve the precipitation a little bit. But I'm not expecting anything dramatic. I'm just hoping for a little bit of improvement in those fields. After that, we want to do a test historical simulation. So that will consist of an extended control simulation and one simulation that spans the historical record from 1850 to 2010 or 2015. We want to do that as soon as possible because we know that our colleagues from CSM have had unexpected surprises from this. They have run into the issue of the model not warming enough when they do a historical simulation with CMIP6 emissions. So we want to test and see if we have the same problem as our colleagues at CSM. If we do have that problem, I expect that we may have another set of critical path activities now with more atmosphere people rather than ocean participation. So get ready for that in case something bad happens. But I'm hopeful that maybe it will work. And if it does work, then we can move on to do the deck plot simulation that we have to deliver by the end of March, which consists of a long pre-industrial control, at least 500 years, a couple of AMOC simulation, and some idealized simulation, 1% per year CO2 increase, up to doubling instantaneous 4 times CO2, as well as multiple members of historical simulation. So I think we have made overall a lot of progress. I'm very encouraged by this last simulation that was put together by the ocean team. And it is possible that we are very close to being where we should be in terms of finalizing the model. But there's always a risk that something will go wrong. And it could be the Earth or indirect effect being too strong, leading to not enough warming in the 20th century. It could be the sea ice going crazy at some point. When we extend the control simulation, it could be something else. So we are much closer to the end, but there's always a risk that something else will come up. That's all I have. Thank you. Any questions?
Chris, this is Matt Maltrude. I have just a quick comment that the Northern Hemisphere sea ice excess that you showed in the time series is almost all due to too much sea ice in the lab sea. And now it's gotten better towards the end of the simulation, but it still is way too extensive. And you can see it in the SST as well. That's where the biggest 5-degree bias is. And so we'll be working on that some to try and fix the sea ice there as well.
Are you concerned about the minimum dropping as well?
Not as much.
Or you think this is just decadal variability?
Yeah, and we've seen this in pretty much every run. The seasonal cycle in the Northern Hemisphere sea ice tends to be pretty significantly larger than the data, at least current day data, right?
Yes, and the data plotted here is the climatology, so it doesn't show year-to-year variability.
Right.
Yeah. Okay. As long as we don't see any trend going down like this, I think we'll be okay.
Yeah, we certainly don't want it to completely disappear in the summer.
Which seems unlikely given the cold bias.
Yeah, that's the hope.
That's the bias you were referring to here. And that is better than it was too in earlier versions.
That's true.
Any other questions or comments?
So I do have a general question. This is about your OLR plots, the long wave, if you can go to that. The point is—
The time series? Or the
no,
map?
not the time, the spatial map.
Yes.
So the thing is, you kind of indicated that there were less clouds formed in the tropics of the Western Pacific, right? Is it less clouds, or is it the fact that they are higher clouds? Because if the height is greater, so did you look at the cloud amount and the cloud height for that?
I have not looked at that yet. And this simulation does not have cusps, so we cannot look at the escape type plots to see if that would show up there. But we may be able to look at other diagnostic to identify whether it's really a cloud amount or a cloud height. That's a good point. It could be a cloud height. I think it's not, but I don't have any evidence.
Chris, this is Phil, and Polun might have some comment also, but I don't know exactly what the tuning is for the beta 2 run, but we have occasionally messed with the cloud height. It was low when we went to the higher vertical resolution, and we moved it back up and thought that we might try to move it a little bit higher, the high cloud up a little bit into higher altitudes. So this might just be a generic symptom of the 72 layer model, and we have been messing with and know how to control that if we want to. Olin may have more to say too.
I just want to do a quick comment about the semi-6 emission. It's Cecil, and it's based on our experience with CSM. That I agree with you that it's worth testing. I don't know if you will hit the same problem as us, but it's worth testing as soon as possible in a couple run, because we found out that in CSM at least, doing the traditional present-day aerosol compare pre-industrial aerosol in FKS give us a very little predictive value of what's happening in the 20th century. Because basically by the end of the 20th century, we seems to be fine. But what we see once we switch to the semi-6 emission, there is a big decrease of the surface temperature that happened in the period like 1950 to 1980. And after it warms again, but
okay.
Yeah, just to talk about the very little predictive value that we found to do FKS for this. Because when you look at the... Sorry?
Have you tried to do F cases with maybe instead of using 2000, using 1980 or 1950?
We did 1960 and still it's not... Yeah,
it still was not
help to predict so far. And if you find a method to predict what the 20th century simulation is going to do, it will be very interesting for us too. But
I think we're going to go with a more direct approach and do the historical simulation first, and then deal with what we find.
Yeah, with what we have been doing. What we have been trying also is to do different kind of simulation, historical simulation that will start later in 1930. And it seems that there is some predictive value, but it's not like really clear, because we didn't want each time to redo a simulation starting from 1950, and we have tried different setting when we start the couple simulation later. And there is some predictive value, but it's not really completely, it's still a little bit hard to tell what's going to happen. It's better than doing FKS, but it's still hard to predict. Yeah, it was just to share our trouble.
Thank you, Phil.
Because we have been spending like basically months on this.
And are you getting closer to resolution, or?
There is some improvement that we got by changing the auto conversion, but yeah, it's still not. We are still not completely there yet. We are closer than we were a few months ago, but this semi-6 emission really stopped us in our effort for months.
Cecile, this is Phil again, and I have been talking with Xiaocheng and Ruby a bit about it, but I thought it might actually be really useful, and Chris, I think I might have mentioned also, that we might ask you and all of the ACME team members plus, or the E3SM team members plus the Andrew, perhaps to give us a talk one time on what you've been learning, just so that we could identify what problems you found and what solutions you found to those problems.
Yeah,
might
I
be
think it would. Yeah.
for the whole group, but I was certainly thinking about it for the atmosphere, but maybe everybody on the in 3SM would be interested in hearing about it. So,
Yeah, I think at least the atmosphere, and for the rest of the group, we can check with them.
okay. I'll talk to Chris about it and we can decide.
Okay.
Thanks.
So we are past our allotted time, so maybe we should stop here unless there's anything else urgent. So again, I would like to encourage everybody to look at this simulation and do any analysis that you're interested in looking at, and report to us anything good. We want to know that, as well as anything that you think is worrisome or troublesome.
But it was a very nice presentation. Yeah.
Thank you. Dave or Renata, do you have anything to add?
I don't.
Thanks, Chris, from DOE.
Okay.
Thank you.